This is a work in collaboration with two other PhD students, Emma Albertini and Emanuel Panella. So here's the plan of my talk. First, I'm going to give motivation for why we expect from discrete quantum gravity that particles should deviate from their geodesic motion. Then we'll get to the main formalism, which uses the kinetic theory in curved spacetimes to formulate the unique covariant Brownian motion of massive particles in vacuum. Finally, we'll get to the applications of this idea in cosmology and in particular for dark matter particles, and we'll see its implications for the SA tension. Here's the main idea. Spacetime might be discrete at Planck scale. But so far, we have had no direct empirical evidence for quantum gravity in general and discrete theories of gravity in particular. So a natural question is, where should we look for signs of such a discreteness? For the current talk, I'm going to focus on the rather simplified case of the motion of point particles on a classically discrete spacetime and see whether there are any defining signatures that we can look for in observations. If we propose that a spacetime is discrete, then we actually lose access to the infinitesimal differentiable structure of a smooth manifold. So that when we are building particle propagation models on such a discrete background, then we can no longer refer to such a thing as a geodesic, but we should replace it by some kind of a combinatorial notion, like the longest chain between two given events. So there are a couple of models that actually do this, and they all have two generic features. So first of all, they show deviation from geodesic motion, as you can see in this picture. And second, this deviation seems random to us because we don't have access to the underlying fundamental discrete spacetime. An important question at this point is that, is there a model-independent universal description of such a phenomenon, similar to the usual Brownian motion of particles in a fluid, where we don't actually need to know all the microscopic details of the fluid, but we can describe the Brownian motion by using a single diffusion parameter. In order to answer this question, from now on, whatever I will say will be independent of any theory of quantum gravity and will hold at an effective level on a continuous spacetime. And here's the main claim, that if you enforce general covariance on the equation that governs this deviation from geodesic, then this equation would be uniquely fixed and it is described by just a single additional free parameter. In order to see this, let's take a collective of particles described by some distribution rho in a phase of space P. So we know that rho must satisfy the well-known Fokker-Planck equation, where there is this drift or transport term as well as the diffusion term. It was noticed independently by Sorkin and Graham that this object KAB is in fact a tensor in the phase space, in the sense that if you change the coordinates of the phase space, it transforms like a tensor. And this will be important for us when we want to find K, because our main objective now is to actually find these objects KAB and BA. In our particular case, the phase space is given by this gamma m plus, which consists of spacetime points x and momentum p, such that this p is restricted to be on the mass shell. So p squared is equal to minus m squared. And so the coordinates of the phase space are given by x and q, where this q is the physical momentum projected on some given tetrad. Now, if we enforce the matrix K to be a tensor and also to be positive definite, then it is actually quite restricted. So first of all, its spacetime part has to be zero. K mu nu is zero, and also the cross terms between spacetime and momentum have to be zero. It's only the momentum part of this diffusion tensor Kij that can be non-zero, and that has to be proportional to the inverse metric tensor on the mass shell. So the mass shell is a hyperbolic space, and its metric It's inverse metric actually. It's given by delta ij plus qi qj over m squared. And one can show that this kij has to be proportional to that by some constant kappa, which you can think of as the diffusion constant. Now, if we plug this diffusion tensor back into the Fokker-Planck equation, what we find is a modification to the Boltzmann equation by some diffusion term on the right-hand side, which is proportional to this constant kappa. And it also has this Laplacian operator acting on f, the distribution function. And this Laplacian is not on spacetime, but it's on the momentum mass shell, which is, again, a hyperbolic space, and we denote it by H3. And this is what we call the Swerves equation. Now, corresponding to any Fokker-Planck equation that describes the collective behavior of particles, there exists a set of stochastic differential equations that govern the behavior of single particles or single trajectories. So in the case of Swerves, we can actually write down these stochastic equations, and they turn out to be modifications to the geodesic equation. So here, instead of these terms being equal to 0, we have corrections on the right-hand side. One of them is just a drift term proportional to the momentum and the constant kappa. And the second term is a Gaussian noise term, such that its two-point correlations are again given by the diffusion tensor K. So here you can see that, again, the inverse metric tensor on the mass shell is appearing, g mu nu plus b mu p nu over m squared. And this is the unique relativistic Brownian motion that we were looking for. There's also an intuitive way of understanding why this drift term appears here. So if our particle is at rest, then for doing a random walk on the mass shell, it has equal probabilities of going to the right or to the left. But if it has a non-zero momentum, then the unit disk in the hyperbolic mass shell is more skewed towards higher momentum, and that's the reason that causes this drift term or the bias term to appear here on the right-hand side. Here you can see three different realizations of the stochastic differential equations that we had. So first of all, the random walk is actually happening on the mass shell, and it's only through its indirect effect that we can see the deviation of particles from the geodesic motion on space-time. So this is unlike the usual Brownian motion in fluids, where the actual random walk happens in real space. But in our case, the motion in space-time is actually differentiable, and the random walk is happening on the mass shell. Now we can get to the application of this idea in cosmology. So we apply it first to dark matter particles, but in principle, this should be applied to all of the massive species. Since dark matter particles are the most dominant of massive species, that should be enough for us for the moment. The Swerves equation now corrects for our cosmological background and perturbation equations. So for example, the continuity equation for the dark matter density gets some correction on the right-hand side. And we can see that this constant gamma appears here, which is proportional to the diffusion constant kappa. And it has also this factor of m squared here. And it turns out that in all of the cosmological equations, it's actually this parameter gamma that appears. So that from the cosmological data, it's this parameter gamma that gets constrained. And it also has the same units as the Hubble parameter, so you can think of it as the diffusion rate. Here, I just want to say a few words about how we balance the total energy momentum conservation. So when we are saying that this Swerves effect is happening, dark matter particles are spontaneously gaining energy, and we should mention where the source of this energy is coming from. So ideally, this should be described by some stochastic term on the geometric side of the Einstein equations. But for the moment, we don't have such a formulation. So we treat this problem phenomenologically, and we propose that dark energy has to have an imperfect fluid energy momentum tensor, and it's the dark energy that's sourcing the extra energy that's going to dark matter particles. The next step would be to solve for the background and perturbation equations for dark matter. So here you can see the Swerves equation, again, written for the perturbations to the distribution function. And again, we see that this Laplacian on the momentum space is appearing here. And so for numerically solving for that equation, we use the so-called generalized Boltzmann hierarchy, where we expand the distribution function not only in Legendre polynomials, but also in powers of the velocity, so that this is described by two indices, n and l. And this introduces an infinite set of coupled ODEs that should be solved simultaneously. But in any practical calculation, of course, the indices n and l should be truncated at some finite values. And also, the relevant moments for the Einstein equations are only the lowest moments of the distribution function, as you can see here. So here's the result for the dark matter density contrast versus scale factor. So during matter domination, we see the usual growth of structure proportional to the scale factor, but at some point a transition happens and the dark matter density contrast starts to drop like a power law. So this is some kind of a smoothing of the perturbations. So the structures are getting washed away due to the effects of diffusion. And it would be also very helpful if we could find some analytic behavior for the cosmological quantities when the diffusion starts to become important or starts to dominate. So this is what we're going to do next. Surprisingly, it turns out that we can actually analytically solve for the Swerves equation for the distribution function. So the solution in non-relativistic regime looks something like this. So there's a Sachs-Wolf-like term which accounts for the initial conditions. And there is an ISW-like term which accounts for the gravitational source terms. But more importantly, there are these exponential factors that are only caused by the diffusion effect or by the Swerves term. And we're going to focus on these terms in the next slide. So first, we should remind ourselves that at the background level, it's only the ratio of the diffusion rate to the Hubble constant that's important. So if this ratio is small, then the effect of diffusion can be ignored at the background level. However, at the perturbations, the picture is very different. So you can see that in the exponent, there is this factor a gamma k squared times conformal time cubed that appears. And one can actually show that this is a function of the diffusion length divided by the co-moving length scale of interest. And this is telling us that whenever the diffusion length becomes comparable or much greater than the length scale we're looking at, then diffusion is important or dominant at that scale. And the effect is through this exponential factor, which exponentially suppresses the effect of initial conditions. It washes away the initial data. And also in the ISW-like term that we had, it clears the effect of the potential at early times, and it's only the behavior of the gravitational potential at very late times that contributes to the integral. And then one can use a saddle point approximation for that integral to actually show that, for example, the dark matter density contrast has such a behavior in the strong diffusion regime. So it's proportional to the gravitational potential, but it's decaying like a power law. And this is exactly the a smoothing or washing away of the dark matter structures. Next here, we can see the linear matter power spectrum for increasing values of the decay rates. We can see that the effect is the suppression of matter power spectrum at small scales. And as we increase the value of gamma, the value of sigma 8 starts to decrease. And on the right, we can see the relative suppression of the matter power spectrum to the power spectrum of lambda CDM versus scale K for the best fit set of parameters and for different redshifts. So we can see that at, for example, redshift 3, where the Lyman alpha data is important, there is at most a 20% level of suppression in the matter power spectrum. But as we come to lower redshifts, for example, at redshift 0, there is a very strong suppression of the matter power spectrum. And this is in contrast with many warm dark matter models, where the main physics actually happens at early universe. And so the relative suppression of the matter power spectrum at late times is actually redshift independent. And finally, here we can see the MCMC results for these cosmological data sets. I just have to mention that for the kids case, we don't actually use the full likelihood, but we just use their measured value of S8 as a prior for our MCMC. And also different methodologies by KISS or DES yield different levels of tension for S8 in the case of lambda CDM. And so for the two cases that we checked, a 1.9 sigma or a 2.6 sigma tension in S8 can be reduced down to just a 1 sigma difference for the case of Swerves. And here we can also see a mild 1.2 sigma preference for a non-zero value of the diffusion rate. And the best fit actually turns out to be around 10 to the -6 times the Hubble constant. So these results should be considered with some caution because we have so far only modified the linear perturbation equations. And a definite confirmation that the model can actually resolve the S8 tension requires us to do n-body simulations and fully go to the nonlinear regime, which is something to do for the future work. But so far, the model seems very promising in addressing the S8 tension. So here is the conclusion slide, and finally, thank you for your attention.